Today we're going to talk about atoms and electron domain geometry. Electron domain geometry examines and describes the probable arrangement and locations of electrons surrounding a central atom of a molecule or ion. When we talk about electron domain geometry, we are referencing bond domains. Non-bonding domains are not included in this conversation. So let's start with talking about what an electron domain is. An electron domain is the region of space surrounding a central atom in which there is a high probability of finding electrons. Electrons don't just circle a nucleus in a perfect circle. They travel around the nucleus in what is called an orbital. An orbital is a cloud-like region around the nucleus that is mathematically described based on quantum physics and mechanics. We can use these formulated equations to predict with some level of certainty the probability of where an electron might be at any given time within that orbital. So when we know that electrons have a negative charge, and we can observe that objects with an opposite charge are attracted to each other, and objects with the same charge repel each other. So an electron will naturally repel away from another electron. So to simplify this, if you can imagine two electrons traveling around a nucleus, the two electrons will always be as far away from each other as possible. So now if we complicate that relationship by adding the electrons from a bonded atom to the molecule or ion, we see that we complicate that relationship and that those probable locations or domains of the electrons become more complicated. Fortunately, we can use balloons to visualize these relationships. Let's start with CO2, carbon dioxide. This molecule is what was referred to as an AB2 molecule, in that we can use A to represent the central atom, which in this case is carbon, and B to represent the bonded atoms, which in this case is oxygen. And the integer X refers to the number of bonded atoms. So this would be, so ABX refers to all those numbers, and in this case it would be an AB2 molecule, CO2 having two bonds to the central atom. Okay. Now you can see that the balloons are all connected to the central fixed point. This represents the central atom, carbon. The electron domains repel each other and will arrange themselves as far apart as possible, just as these balloons are. We call this bond geometry linear. Now, if we add another bond to that linear, we can. So let's go ahead and add another bond in here. Add that third bond to the central atom. Remember, the center here is that central atom. So this isn't three atoms, this is actually four. You've got your central atom and three atoms bonded to it. If I can bond this one here. Somehow. I feel like a balloon artist here. All right. Can't read that. Now you can see that when we add another bond, that the balloons arrange themselves so that they are oriented away from each other. This domain geometry is referred to trigonoplanar. We also We also see a similar geometry when a lone pair occurs around the central atom, such as with H2O. When there's an unbonded lone pair in the electron on the central atom, if you imagine my hand is that lone pair, then that pair of electrons influence the electron domains and form a similar geometry, which is referred to as bent or nonlinear. And you can see that that sort of forms a similar geometry when there's a lone pair attached. Now let's see what happens when we add a fourth bond or lone pair to the central atom. So here we have that trigonal planar, and we're going to add a fourth bond to that central atom. There, so now you can see that all of those domains are oriented away from each other. And we get an electron domain geometry known as tetrahedral. Okay? When we add a fifth bond to that tetrahedral, we get this shape where we have that familiar triagonal planar shape, which is similar to this, with two end domains creating a geometry known as trigonal bipyramidal. You can imagine that if we sliced this shape in half, we would have two pyramids attached to each other at the bases. The geometry that we get when we have 6 electron domains is called octahedral. And this is where we get that square pyramidal. So if we slice this, we'll get a square pyramidal or a square planar when the domains are the results of lone pair electrons. So you can see that the electron domain geometry is impacted by the number of bond locations or lone pairs that occurs around a particular central atom in a molecule.